Okay, so I guess I need to say a few words about Ben. Who doesn't know him in this room? All right. So it seems very necessary. So Ben is our alumni from WINLAB. How many years did you spend here?
A while.
Okay, good. So he did a wonderful thesis, has done excellent research, has mentored a lot of students while he was here. And the pig tags that you guys occasionally play with were his babies. And he also sort of, when he was a student, he took me to Maker Faire. And that was actually my first trip to such places, and that's a whole new world. And we tried startups together, we tried Kickstarter, so it was a whole adventure, which was very pleasant. And I still remember that during your defense, I forgot to shake your hand. So after you passed, I'm sorry for that. All right, so after that, yeah, I was...
Grammatically, that could have implied you're sorry for him passing.
Oh.
She was too excited to take a picture.
As well.
Right, because he was wearing a costume at that time, right?
It was a formal?
Yeah, formal suit, and emulating the defense scene. And so I got so excited to take pictures, forgot to shake his hand. All right, then after that, he actually taught at Rutgers. Still, students liked him. You were teaching programming methodology, embedded programming, all those things, right? Then after that, he joined NVIDIA and working on driverless cars. So that's what he's going to talk about today. And right now, apparently, he's an expert on machine learning. So those of you who want to learn machine learning can talk to him afterwards.
Yeah, so expert means I've been doing it for a year and a half. So anyway, at some point our group made a paper, and I guess we presented it at NIPS in a workshop, but we called it End-to-End Learning for Self-Driving Cars. So let me give you sort of an overview of what our project is at NVIDIA. So basically the goal is we're going to take a bunch of data from people, so people drive around. We record sensor data, in this case typically a camera mounted in the car, so it's basically recording the road. Actuator data, that generally means steering, how fast is the person going, are they braking, things like that. And then we train a network, so we put out the data into some data set, we train a network, and so the way training works, if you guys know nothing about neural networks or sort of machine learning like this, is you give it an example, it has some output, and then you look at the difference between that output and what the human actually did, and then you correct it. You say, no, you were wrong by this much. And then you do it again, and then you do it again, and then you do it again, and again, and again, for a long time, and then eventually it gets very good at predicting with this image, here's what the person would have done. So just, and I'm going to talk about it a bunch, so just so you know, we use convolutional neural networks, and so I know this is a networking lab, so there's not a huge background in it. You know, the idea of neural networks is that you have a thing called neuron, which has some input and some output. And what it's really learning is it's adjusting some weight or some bias. So it's learning, I need to multiply this input by more, I need to multiply it by less. And a convolutional neural network takes a bunch of those together. So let's say you have some input that's m by n pixels. You have a bunch of these neurons that's m by n neurons. And then each one of these has some input pixel. So that's the actual like pixel value from an image. You put them all together, and then you get some output value. So this is just like, and I'm sure, hopefully people here have taken some course on like image processing or signal processing, where you've done some convolution. So you take this filter, and you move it over the entire image, and you basically get a new output image. So this is the same thing people do for like edge detection with like a Sobel filter. Right? So the idea is the same, but the difference is that all the features are learned. So this idea first happened in the, I guess, late 80s. Rich was there. Actually, wait, I found a cool video that shows Rich. So this is...
That was Rich?
No, that's Jan LeCun. So
we changed a lot.
So this is an example of a handwriting or a character recognition that they developed at Bell Labs.
It's still used to cancel most of the checks that go through ATMs now.
Yeah. So see, it identifies all the numbers, and it's all magic. So this was, they're very proud of this, right, 1993. But the story behind this is that at some point that humans were sitting down and humans were trying to write an algorithm to convert all of these things into digits. So a human would sit there and they'd say, oh, a 4 has a line like this, and a line that goes down like this, and a 6 is like that. And then somebody would write some messed up looking 6 or a messed up looking 2, and then their handwritten code would fail. But at some point, a group at Bell Labs developed something called a convolutional neural network that used those convolutions. And so Rich will show up in a second, so I'll stop.
I was just going to say this doesn't look.
There you go.
This is more like it.
So anyway, what the big advancement right there was that it was all learned. So their breakthrough was that they said, look, if we just have a big enough training set, we give it an example, we give it the output, or it figures out the output, we tell it it's wrong. We do this over and over again. So they take that convolution, there are multiple layers of the convolutions, right? So it's not just one layer of it. That convolution basically produces another image that's slightly smaller after you've convolved it. And then you take another convolution on that, you take another convolution on that. And what happens is the features in the first layers are things like, oh, is it a horizontal line, is it a straight line, is it a curve? But then the later features become sort of semantic abstractions. So at some point, sort of theoretically, it's not really actually clear, but at some point, one of them becomes like a 2 detector, one of them becomes a 3 detector, something becomes a car detector, something becomes like an eyeball detector or a nose detector, and then the higher level one is a face detector. But the really big leap here was that they went from a person saying, oh, I'm an expert at knowing what 2s look like, to saying, I have no idea what 2s look like, I'm just going to use enough data to have this thing learn. And then in 2012 was sort of so for a long time, the results looked really good, but there wasn't a lot of hype about it. Well, there was a lot of hype about it, and then it died off. There was this whole AI winter. Everyone were like, oh, computers suck. And then at some point in 2012, there's an image recognition challenge where somebody, it's called the ImageNet Challenge. They have a whole lot of images, so millions of images. And one of the challenges they do is they say, draw a bounding box around something that you think is the focal point of the image, and say what its name is. So if we took a picture of like, this table right here, we might draw a bounding box around the laptop and say laptop, or computer, something like that. And so they call this like the top 5 challenge. So you have 5 guesses for what the thing is in the image. And so for the first 2 years, everyone was basically handwriting things. They were going, oh, this is a dog detector, this is a giraffe detector, right? Coding it one thing at a time, and they have some error rate. So it's around 25, so they improve a little bit, they're around like 28%, 25%. And then at some point, some people in Toronto, 3 people sat down, they're like, oh, I'll train a neural network to do this. So they took all those images, millions of images, they trained a neural network for 2 weeks on NVIDIA GPUs. And then they got a neural network, they submitted it, and it blew away everyone else. Right? So they dropped 10 percentage error points right there. And from that moment onwards, nobody did hand coding features. It was all neural networks and trained statistical learning models that dominated after them. And so ever since then, there's been a bit of hype about neural networks and AI and all those things. And some of it is hype, but some of it is actually real. So this gets us to driving a car with a neural network. So in 2003, jumping a little bit backwards in time, people wanted to evaluate, DARPA wanted to evaluate, or rather somebody convinced DARPA that they wanted to evaluate whether or not a convolutional neural network could learn to drive a vehicle. And so this is sort of the precursor to all those DARPA challenges that got a lot of attention. So this is just a little tiny rover. It's like this big. It's cute. It's cute. That's what it is. But basically, it's another convolutional neural network. This one is a bit bigger than the handwriting recognition one. So it has about 3 million connections between the neurons, 72,000 learnable parameters. Right? And what they did to train it is they took 225,000 images that look like this, and they just trained it how much to steer left, how much to steer right. And the only goal was to train this thing to just keep driving forever, just don't bump into anything. And the images, if you'll notice, they're kind of bad. These aren't very crisp images. There's like glare in them. Sometimes it's washed out. There's like smudges in the lens. The lens shook around.
Why does that go straight?
Well, because if you go left, you'll hit that. So what they had is a human sat down with a controller and just drove it around their backyard for hours. Like that's, and so this is what I was saying about it's easy to get this kind of data because you just have a human sit down and drive the car around, just don't hit anything, right? You could get your kid to do it if you have kids. If you don't, you could get your grad student to do it. So you just drive it around, and that is the label. So whatever the human did is the training label. And so here's a video of it running. So you see if, like, the video is kind of garbage, right? It's flashing. I think the connectors are bad and stuff. And it's not perfect, right? But at the last moment, it tends to dodge things. And actually, when you think about the information it has, this is pretty good, right? This is a weird environment. It's a bunch of random things. But it's just sort of driving around. So this sort of suggests that convolutional networks should be able to do this at least a little bit. So why do we think, though, that this is a better way to go than somebody sitting down and hand-coding things, right? Because it's very tempting. This is what Google started off doing, all the people from CMU were doing. They sit down and say, oh, I'm going to code a stop sign detector, and I'm going to code a car detector, and lane line detectors, this detector, that detector, it's going to be great, done. So this always works when you know the domain really well, so you know exactly what the input's going to look like. So if all roads look like this, right, that's a good idea, right, because it's easy to identify these, it's easy to test, right? Once you say, I think I have a lane marker detector, it's really easy to test it. Is it detecting lane markers? The problem is, if you write down a system like that, you're relying upon your rules to actually cover all the situations. So now you have another road like this, which is like 50 meters later. This is the bridge over there. Suddenly your lane marker detector, there's no lane markers there, or if they are, you can't see them. All your straight line detectors for detecting lane markers are detecting all these crazy patches. And you could say, oh, we hit this special case, well, it doesn't work. What I'll do is I'll write another detector for the curb, and we'll calculate the exact space here, and we'll infer that there are probably 2 lanes because it's kind of wide, and then we'll choose one or the other, and everything's fine. Problem is, you're not actually writing a simple rule system anymore. You're adding more rules. Every single special case you get to, you add more rules, you add more rules, you add more rules. So when do you actually get to 100% success, or 99 and 5/9 success? And the answer is you don't. Right? So it's just like with handwriting recognition. You'll get most of the things right, and then somebody writes a character slightly differently and it fails. You have to write a special rule for it. We kind of think that this will just keep happening. So anyone who's going down this approach, they'll just keep getting incrementally closer, but they'll never hit, the kind of safety level that you actually have to get when you're driving, right? So why do we think, why now? Why is this the right time to deploy this technology, right? So people have been working on some kinds of autonomous systems for a few years now. And the answer is, sometimes you have to wait for the right conditions, right? So nobody could build an electric car until you have a good battery. Nobody could do MIMO until you have multiple antennas. Nobody can do CNNs for self-driving cars until you have lots of data. So you have to be able to collect lots and lots of data, and then you have to be able to train a model. So right now that means, for us, for NVIDIA, GPUs that can go through lots and lots of data and train a big network with millions of parameters, right? So if we think about it, that Rich could, if he wasn't asleep, could tell you how long it took them to train the CNNs for handwriting recognition, which was probably like I think they usually took a week or 2 weeks. You notice that little Dave rover, when they trained it for another week or 2 weeks. Everybody always trains their model for a week. Right? And the reason for that isn't because you have to train everything for a week, it's a magic number, it's because that's how patient you are. So if you think about it, that model from 2003, if you wanted to train it in 1995, right, wouldn't have taken a week, it would have taken a year. Right? And the models that we train now in a week, you go back a few years, they would have taken a year to train. That's too long to actually verify whether or not something works. But now GPUs are fast enough and data storage is cheap enough that we can get a big data set, train a big model, test it, and go turn right back around, get more data, and test it again. So let me just describe what the actual approach looks like. So a traditional one, and this is where I'm going to talk about the real advantages of this approach. I'm going to sell it to you guys, so you believe me. Traditional approach requires a lot of domain experts, right? So you start off with someone who's a real expert in hand-designed feature extractor, and they train a classifier using that data, so you use a little bit of training, but then you don't trust it. So you have somebody else build a cost map from it. So you start off with, basically this person builds a feature extractor, so they hand code, these are the features we care about, and you train a classifier for lane markers, you train a classifier for stop signs, you train a classifier for stoplights, you train a classifier for pedestrians, for bicyclists. And I'm completely serious about this. People have these image sets with 20 different things that you have to recognize, including like telephone poles, right? So everything. Then you have somebody say, well, what's the proper way to deal with every single one of these different objects? Right, so now you have to have some expert who's maybe on safety, on driving, so how do you deal with each one? What's the optimal way to do this or that? Then you have a path planner. So this expert has to figure out how can the car drive through this scene like this. So they have to sit down and maybe they have to simulate it. Well, in this situation, maybe it's wet, you have this much traction. So they make all these controllers and lots of equations, and it's very complicated. And then you have finally you're actually driving, right? But this takes this is a big team of people, right? And then all the parts have to work together perfectly or it fails, right? So we replace it with this. So we have a camera image, and then we have our training data, and it's trained a feature extractor and the controller. They're both trained together, so it's one neural network, and then it drives, and that's it. Right? So how many experts do we need for this?
So are you guys the only ones who are doing this way? So there are competitors which we don't need to mention. Are they doing the traditional approach?
Well, there was George Hotz, who made a big deal about doing this too, and then he was like, oh, this is hard. Actually, he said, oh, rules, I can't deal with them. So what happened was, he was training things like this, and then at some point he sent out like I think it was a tweet or a post where he was like, oh, the National Highway Transportation Authority wants me to publish safety guidelines, and this is too much regulation, then he dropped out. So I think right now, Audi's doing it because we're working with Audi, but most other people are using the traditional approach.
You know, I guess the Google's works pretty good as well. No.
Well, how well does it work? So let's talk about for a second about this. If you remember, one of the accidents the Google car got into was when it ran into a bus.
Yeah.
Right. So why did it run into a bus? So it's driving along the road, and it moves into the gutter so it can make a right-hand turn because it sees there's traffic in front of it. So somebody coded when there's traffic, but you want to make a right-hand turn, you could go over to the shoulder to make the right-hand turn. So it does. And then it sees, oh, there's something in the drain. I think it was like a sandbag or something. So then some other hand-coded thing says, oh, you can't drive over that thing. You have to get back to the other lane. So then it decides to get back to the other lane. And then at some point, somebody hand-coded, oh, don't be too passive. At some point, you have to go. And it decided to go right when there was a bus. And the bus, of course, said, that's absurd. That person will never try to cut me off. I'm a bus. And the Google car actually just ran into the side of the bus. So it's not like it got into the lane and then got hit. It just hit the side of the bus. Right? So I feel like that's the kind of failure you get when you hand-code one rule and then another rule and then another rule. But intuitively, no person jumps in front of a bus anyway, because buses are really big and they can't stop very well and they can't see you, right? So you're more likely to be hit by a bus. I'm more careful around an NJ Transit bus. I don't know about you, Yanni. But so a lot of these systems, so like I said, I think the problem is not getting something to work pretty well. The problem is getting those 5 nines of reliability.
Well, yeah, but
How do you show the 5 nines with this approach?
So I'll talk about validation later, but the real answer is you have to, at some point you have to drive it on roads to some extent, but you also have to you can use the data itself to validate. But we have a simulator that we use for that.
yeah, but how many miles did they get before they got this bus accident? So you could measure it by miles
they
per
claim a lot.
accident
So
or accident per miles.
So the real problem with this is that it's not about, so for instance, if we took our system right now, which is not ready, but we took it right now, we could drive up and down the Garden State Parkway and never have an accident. Because the Garden State Parkway isn't a very eventful road. It's a highway. Everybody's kind of just driving fast. Like, you don't expect a bunch of kids to be playing in the middle of it. There are mostly lane markers for the most of it. Some of it has really poor lane marking, but that's not really that big an issue. So the question is, where do you get your million miles? Yeah, so you have to say what happens when you're actually in a really challenging part. So if, let's say you have, a lot of these systems work by having very, very high definition maps. And high definition maps when you have, an exact centimeter level accuracy everywhere. You're basically self-localizing yourself. And then you're basically just like a train. You're driving on rails, like someone's pre-programmed the route. So that turns it into a different class of problem. But then when you're in the real world, right, somebody puts up a construction site, somebody throws down a bunch of cones, right, your map doesn't have that in it, what do you do? I think those situations are the ones where you really have to evaluate these different driving strategies. Because I'm pretty sure, so for instance, Ford had a cool demo where they drove in the night in the desert with their lights off, and it's a cool demo, but they were driving with LiDAR. Right, and LiDAR doesn't care if the lights are on or off, so it's a cool demo, but what they're demonstrating to the people is, or what they're actually, the technology they're demonstrating is actually something different than what you might infer they're demonstrating. Right, so it's hard to evaluate exactly where the different companies are because they don't release what their approaches are. But I think in general, the more you rely upon somebody hand-coding something, the more you rely upon a map that's exact, and that's really what you're relying on, the harder it will be to hit extremely high reliability. The more you'll have to say, oh, it's a construction area, the human has to take over. Or like, oh, the road is different than my map, the human has to take over. And that's okay, that'll reach some level of autonomy. But we think to reach full autonomy, you have to do more of a machine learning approach.
So, we had a question on your feature extractor.
Yeah.
So, how much do you include features of the recent past in the feature set, or no? Like,
I mean, is there
conditions of the
history
recent
involved?
past, like some kind of history, right? Like, I just braked 2 seconds ago, or something. You know,
So
like,
this model that
or
I'm
is it
gonna
instantaneous? Is it like stateless?
yeah. So the videos I'm going to show the car driving and the model I'm going to talk about has no history.
Okay.
But to do things like lane changes, we have history.
Okay.
Right. So there was if anyone watched like the CES video, it shows the car changing lanes, and for that you have history because you have to know where you are.
Yeah.
Right. You have to know like I'm actually changing lanes left. Otherwise, you'll get to the middle and you won't know which way you're
Right,
supposed
but it needs some intentionality and then some.
Yeah, so you have to have
history or
some
something, yeah.
some context,
Okay,
basically.
okay.
Yeah, same thing. Like if you're going to stop at a stop sign, you have to have some context to know that you actually came to a stop before you go again. Yeah.
So features evolve, oh, go ahead.
Why are you only using a single front-facing camera?
So this is just for driving. For lane change and stuff, then we have side cameras on the mirrors.
Okay.
So this is describing
This is
a
for
network
lane-
that we had a few months ago. So like the current one's a bit different.
And so
This is for lane
I-
keeping, right?
Yeah,
Or
this is lane keeping.
only lane
Yeah,
keeping.
only lane keeping. Yeah.
And what should I do at night with your system?
Turn on your lights.
All right, is that sufficient?
Yeah.
How does that work?
That works.
All right. Have you looked at the
Raining
crash,
lights.
the China crash for autopilot from Tesla, where there was a color illumination issue? It was basically a white object with a white background, or that was the Florida
That was the
case?
Florida one.
Yes.
Yeah.
No, they had an orange object with another orange background, and
Oh.
you couldn't distinguish, and it went right into the orange construction truck.
That's a. I'm not gonna say that's a stupid problem. That sometimes those errors I think have to do with particular corner cases that.
The corner case is life or death.
Well, no. So that has to do with a corner case with their system. I mean, so I think the Florida crash didn't have to happen either. But there's always a trade-off that you make in a release system, and I think they made a trade-off between safety and usability.
So Tesla then went back and decided to add on, because they were only using cameras.
They
Yeah,
no,
went
they
on.
were using radar. They always had radar.
But- And now they are using multiple sensors,
Yeah.
so.
Yeah. So I mean,
They
there's
weren't- No, they weren't using radar in that case.
all their cars have radar.
Well, so
Now they're using radar.
All their cars have radar, but what,
Which they were
what
collecting
was,
data for.
what was that? What was the question is there's one specific component that does the automated emergency braking. And the question was whether that algorithm uses the radar input as well in addition to the camera. Right? So
Yeah.
that's the confusion here.
Yeah, and that's secret to Tesla.
Yeah.
Yeah.
Well, but what's not secret is their press releases lately, which have said that they are now combining radar and vision.
Yeah. So
But-
their
but
problem
are you
before.
claiming that cameras are enough, or?
No.
Yeah,
So
that's
this
just
this
would
yeah,
apply
to
no.
radar
So
as
this
well,
is
right?
this is just so this is an example of a lane keeping system. So there's no reason why your neural network couldn't have additional inputs. So we don't I don't particularly like LiDAR because it's so expensive, but there's no reason why you couldn't combine LiDAR with your cameras. There's no reason you can't use radar and ultrasonic and all the traditional advanced driver assist systems. There's no reason why you can't combine them. And there's also no reason why you can't have traditional safety systems with a neural network. Right? So in the same way you're driving your car, your system still has like ABS, right? It's not like we would disable everything else just because we say the neural network would do it all. Right? So there's no reason to take away all the safety gains that people have already made with other systems.
Did anybody look into efficiency or which one is better to use or?
In which case? Oh, like which sensors are better?
Yeah.
Yeah. So
I mean,
that's
take
something.
LiDAR or
Yeah.
camera.
So the attraction of cameras is that if you have if you're going 65 miles per hour and somebody jumps over the median, they're coming at you at a relative speed of 128 miles per hour. So if you have a braking time of like 3 seconds or a swerving time of some amount of time, that's when all these things matter. So the only answer to that right now is generally cameras. So radar have a latency, which means that the latency is too much, so you'd hit it. LiDAR have very low resolution, so you wouldn't see it when it's too far away, so you'd hit it. So right now, cameras are the thing that would solve that. So whatever driving system you have will probably have to have cameras, so that's why we started with cameras. And then we'll add in whatever else is necessary. But since we know that you have to use cameras anyway, we may as well just start with cameras.
Do features have persistence? Do they have evolution, or do they Are they de novo every time you got a new data set?
So yeah, we start over with a new data set. Every time.
You don't have a sense of evolving features that are more effective as time goes on.
No, I mean we generally train from scratch when we get an entirely new data set. We just actually add data to the data set and then retrain. We've tried things where we pre-train it with certain data and then train it with other data, but we haven't seen any difference. Generally, if you retrain it from scratch, you'll end up with pretty much the same network anyway. So there's generally new data doesn't add something fundamentally new. You're just fine-tuning the end result.
But that suggests that, eventually you stop training.
Yeah. That's what car companies want. They don't want you to train while you're driving, because then they can't prove the safety of something. This is this interplay between research and reality. Like, no car company wants something learning online, because then they can't guarantee that the test it passed, it will still pass.
But it's interesting. I mean, that suggests that you would, at some point, get to the full set.
There's always corner cases.
I know,
Yeah,
but I'm
there's-
saying
There's going to be an
that
iguana on the
approach-
road
this-
once in a
this
while.
is-
but that approach guarantees that you will.
6 nines is 3 minutes each.
It would be nice if there was a really good information theory person who could sit down and say, these are the number of bits of information in all of driving,
That you need.
and that would be great. But everyone I've asked that question to is like, what are you talking about?
But there isn't. There's a power law distribution. Weird things will happen. A meteor will land on the road once every 20 years.
But the question is the statistic of a meteor, is its appearance and your behavior different from a tree falling? Right? How different is it from other things that you've seen?
That's what I'm saying. I mean, you can arguably map everything to a corner case.
Yeah, so at some point, right, the neural network generalizes pretty well. Like at some point, how well has it covered everything? Now the corner case is 100 years down the line rather than once a year. Probably the more practical question is, when is it better than a human? That's probably the more practical question.
From an insurance point of view.
From an insurance point of view, yeah. Well, also the car company, they want to say it's better than a human. If they're going to sell you a vehicle, they can't say, drive this vehicle that will drive itself. By the way, it's worse than you are at driving.
Do you have any idea how you demonstrate that you're better than human?
Yeah, so this is later slides.
Okay,
Yes.
I'll wait for that.
Okay, so
Also, where is my input into all of this?
what do you mean, as the human?
Yeah.
You
I mean, I'm
This
talking
is-
about style, right?
That's a completely.
I mean, I would walk out of the car if it drives like.
So this is actually something we've talked about. So for instance, the training data we collect in New Jersey is with New Jersey drivers. The training data from California is California drivers.
Oh my
and
God.
there is a difference. And so we've talked about this, but for right now, let me defer that question for the future.
But that just controls the honking part, right?
Yeah, you just honk. You honk at everyone.
You could take
Okay.
the American car to Germany, right?
Yeah, it'll be great. So anyway,
Pile up on the highway.
the point of this slide was that it takes, in terms of domain experts, you're taking this gigantic team of people and you've shrunken it down to still a team of experts, but they have to be experts in many fewer things. Okay, boom. All right. So let me go over just how the system works. So what we do is we go out, we go driving around, we collect data. So we get a video like this, and we then basically replay the video and we label it, but not by, so traditional things, like I said, if you're training a bunch of detectors, you'd have to label, this is a lane marker, this is a sign, that's a telephone pole, that's the curb. So we just do very coarse labeling, so we just say, you're driving, and it's useful, and here's the road type, here's the weather and the lighting, and that we use so we can rebalance the distribution of training data, so it's not like 99% day on a highway. So we rebalance it so it's not too biased. And then we mark, what was the human doing at the time? Were they driving stably in the lane? Were they turning? Were they changing lanes? And that's so we can choose what we're training the network to do. And then as we train multiple things, the training strategy changes slightly for different tasks. So a strategy that we use for, let's say, augmenting the images when you're driving straight is maybe not appropriate when you're making a turn. So we go through, and let me just talk about augmenting the data, because I just talked about that. So it's not feasible for a human to drive erratically on the road, but we still need training data. We show the neural network how to correct if you're in a bad position, right? So you imagine at some point the neural network will make some small mistake, it'll be off-center in the lane, and you say if the human was never off-center and the neural network didn't know what to do, then it would just crash, right? Which is bad, so we don't want that to happen. So what we do is we simulate being in different positions on the road. So imagine you start off with some image that looks like that. What we can do is we can simulate a shift. We basically sort of do a perspective transform and shift over the pixels. We can rotate the image by taking to the top of it, and you do a perspective transform on the pixels. And then in the end you get another image that looks like you're off center and rotated. And then we say if you see this, we use basically a simple augmentation formula to say here was the human's original steering angle, but if they were over here, they'd want to intercept with their original trajectory. So we augment the human's label, so the training label, and we augment the image, and this basically multiplies our training set and teaches it how to correct itself.
Can you train in a simulator? I mean,
Do you trust a simulator to be real?
some of these video games look pretty real.
They look
so-
pretty real.
Yeah,
They
I
don't work
know.
in real life.
Okay.
So one of the problems is the real world has a bunch of, imagine even if it's just like your camera artifact. So
Yeah.
let's say your camera gets lens flare or glare on it. But there are too many things that you didn't think of in the simulator. So this gets back to somebody sitting down and hand coding everything. Now you have to have an expert on the statistical distribution of like farm animals on the road. Right? This is the kind of thing you're trying to avoid doing, like, right, just like every once in a while you'll get some rare event, like somebody opens the rear window and all these papers go flying out. And there are papers all over the road. This may happen like once a year, once every 2 years, but unless you think to do that in the simulator, you won't have that training data, the car will encounter it, and then it'll just crash. Right, so the advantage of getting real data is you get a real sampling of the true distribution of what kind of garbage is on the road. Right, so the simulator is only as good as the person's imagination, whereas the real world is the real world. We trust the real world data, we don't trust the people who made the simulator. Although people, yeah, have trained models on like Grand Theft Auto and stuff, and then it drives in Grand Theft. I would not trust that on the real road.
GTAs.
Yeah. So anyway, this is what the network looks like. So it's multiple layers of convolutions. So it's actually a very typical network, if anyone has looked at neural networks like AlexNet or anything. So it's a bunch of neural networks of convolutions. So think of these as each producing an image, just like a filter that finds edges. So each of these produce bunches of images. So this makes 24 new images, 36, 48, 64, and then we flatten them down, and we put them all into a fully connected network, which is sort of the more stereotypical classifier network. And then it shrinks it down in a sort of pyramid-like thing, and it has one output, and then output is the inverse R. And if we were doing speed, then it would have 2 outputs, and we'd make it a little bit bigger. If we're doing left and right lane changes, then we have to add a little bit more to it. So you imagine as you have a more complicated series of tasks, it becomes a little bit more complicated. But this would be a basic lane following network. So it's about 250,000 neurons, so that's 250,000 trainable parameters. So it's sort of comparable in size to AlexNet, bigger than Dave, that little robot that dodged things, but smaller than some of these modern neural networks that do, like these ones that people are training for like ImageNet to get super high accuracy on those things. So as we get to more complicated tasks, this network will get bigger too, but it's not appropriate to have a network that's more complicated than the task.
So what determines how many layers, and, I mean, is it just
Hand
an
waving.
art of?
It's-
No, but there has to be an art.
I mean,
Yeah, well, so
what's
I guess the right
intuition
answer,
about how people do it?
the right answer is there's this cool thing that I like to call the Larry curve. But basically, if you have some idea, actually this is not the right, is there an eraser?
Don't even think about writing on the screen.
Okay.
That's what you looked at. No.
I'm just looking over there
It's
for
when they
one-
don't think about
Okay.
it that it's a problem.
Okay, so if you think about you have, so let's say you have some loss or error, however you want to think about it, and you have some amount of training data, so some number of samples. Oh. Well, now I'm already committed to writing this tiny graph.
Let's play it out.
So I hope everyone can see it. So as you add more training data to your system, you train it and you test it. So imagine we have some test set. The test set doesn't change. So when you start with, I end up with an infinite number of samples. So we start off with some test loss that's like infinitely high because you have 10 examples. There's no way it does it. You train your model and you see a loss that comes like that and then it bottoms out. In the same way, in your training set, if you just look at what was your error on your training set, when you have like 10, it just memorizes the 10 and it gets it 100% right. And then at some point, you'll get a curve that comes up like this. And two approach each other. And you learn multiple things from this. So one, the error where they meet is just as good as this model is going to do on this data. So if you need an error better than that, then you have to have a model that's somehow better. Either it's bigger or you change the structure somehow to make it better. But from this, you can also see, are you actually using the full capacity of your network? So let's say you only have this much data, and you're only up to here. You could see, oh, you just need a little bit more data, and actually these two should meet somewhere. And you can say my problem is data versus my problem is my model isn't big enough. So this is one of the ways you could evaluate what's the appropriate size of my model for the amount of data I have.
Did you use that approach, or did you just randomly
No,
decide?
this is Canva.
Oh, okay.
Well, this is what we've.
That says a lot.
Well, this is what we use to verify that this is appropriate. So we've made changes to the model as we've come along. But one of the things we've seen is that for like lane keeping on a highway, you don't need that much diversity before your model starts looking really good for lane keeping on a highway. So some parts of the problem are actually pretty easy, whereas like lane keeping on residential roads is actually much harder just because there's so much stuff. Like there's trash cans and joggers and people out walking their dog and people out, clipping lawns, so they park their big lawn service truck somewhere. So the problem itself changes the way the curve looks.
So you're only using 200 by 66 resolution, right?
Yeah.
Does that mean your computational limited even with all that fancy NVIDIA
Oh,
hardware?
no, we're taking like a tiny percent of the available GPU. So for the more complicated things, we suck up more of it. So we also, for a lot of the demos, we live with a lot of other things. So we live with, another group is doing more traditional things just to show off that we can do them. So this project started as really a research thing, and there were other things that were existing products. So a lot of the things that are demonstrated, they're demonstrating localization using maps and sign recognition and lane marker recognition and all these other things. And so our system coexists with them, so the GPU is running all these things at once.
Why not use the full resolution of the camera?
The full resolution of the camera is 1920 by 1208, which is gigantic. Like a third of it is sky, which has no information. The other third of it is like the hood of the car.
What if you start flying? I mean,
Well, then that's an issue. I guess we'll have to.
I don't know.
So as we get to more complicated tasks, so as you have to like look at signs, after you have to look further ahead, then the resolution will go up and exactly what we look at will change. And especially as you add more cameras, then you have patches for multiple cameras. So you have the side cameras, maybe you have a rear-facing camera to see what's behind you if you're going to do a lane change, right? So then it gets more and more data, so this will get bigger. But it's not appropriate to make a really, really big model
So this
if
is
the task is
it's
small.
a region of interest, or is it subsample?
There's a region of interest that we crop out. So actually we crop out and scale it.
You do scale it.
Yeah.
So which means if you have a small object folder on the road, you might have trouble recognizing that with this
Yeah.
current network.
Yeah, but this is for
But if you
lane
were-
keeping
if
on a
you were
highway.
Right.
Right, so we don't expect somebody to be out walking their dog.
It just runs on a small kit. That's it.
Yeah,
You may have to drive around it, right? So if you
yeah. But this
or
is,
eventually you have to get up to higher resolution.
yeah,
But I
this
guess-
will be bigger and higher resolution. But again, it's not, we don't want to take a giant network and like, for a tiny nail, right? So it turns out that lane keeping on a highway is not that hard a problem in terms of like the size of the network. So.
But presumably you'll need it for more complex.
Yeah, this will get bigger. Not only that, this will get bigger. With multiple cameras, we'll have multiple clone convolution layers, and then it'll become really fancy looking. And for the next paper we put out, we'll have this crazy network with things all over the place. And then it has recurrency too. So for lane changes, there's recurrency. So the output feeds back into the input, so it knows what it's doing. And then it gets, yeah. But this is simple. Okay, so here's what Margaret wants to know. How do we verify that this thing is actually working? So 3 things. We simulate it, but we simulate it with real video. And we use those shifts and rotations to artificially simulate a change in trajectory. Right, so it's always tested with real looking data. So we never test it on like Grand Theft Auto or something. Because we think at some point it would just win in Grand Theft Auto, but that wouldn't be any indicator of what would happen in the real world. We also visualize what the network is looking at. So we try to see, is it looking at the appropriate things, or is it looking at cues that don't make any sense? So we can say,
Very academic.
and then we take it out and we drive it on real roads and we say, what's the performance? And if we find ways to evaluate not just did it fail or not, but did it succeed confidently? So if you can have metrics to measure its actual performance, then you can start to say, this one not only did it not crash, but it also drove very well. Then you can start to say that the model starts looking pretty good. So just to describe the simulator, basically this is the same perspective transform trick I was talking about
Do you
before.
actually need to pass the driving test for the driverless car? Like a parallel parking and stuff like that?
So in New Jersey, the person in the driver's seat is always considered the driver. So we can just get in and turn it on, and I'm the driver if I'm in the driver's seat. And if there's no one in the driver's seat, then you're being irresponsible.
Oh, okay. You are just not driving.
Yeah,
So
then
you
you just
touch the car. It went on its own.
Yeah, you can say the car ran away, but then they'd sue NVIDIA. So We always sit in the driver's seat. We have a very strict safety policy, I should say. There's always a safety driver present in the vehicle. When we go on public roads, there's always a safety engineer with them.
Nice
Anyway.
job.
So anyway, we do the perspective transform, and then we simulate being in a new position. We see what the neural network says to do, like will it correct, will it keep going off? And then we track the position through the course, and we know what the human's initial position was, and we have the neural network's position after it drove the course, and we can say how well did it do. So we identify its autonomy, which is how many times would a human have had to take over. So we have somebody mark where the lane markers were in these test courses, and then we say every time it would have crossed the lane marker, it failed. We have its precision, so if it didn't fail, but it was like always over on the side, that's not so good, so we also keep track of that. And then the comfort, so did it weave a lot? Did it, a lot of jerking when it was braking? Or was it a smooth, comfortable ride? So this is first pass, like if you train a bunch of networks, you run them through the simulator overnight, and then the next morning you come in, you have a bunch of ones that say, oh, all of these ones look like garbage, but this one's pretty good. And then you can take it out on the roads. And the first thing you do when you go in, even on the simulator, is you can make sure it's actually looking at real things. So this is this academic visualization that you like. So what we do is we take the convolutional layers of the network, and you can go backwards through it and see which features correlated with strong outputs. And so we've highlighted those in green. So in this scene, it's highlighted the appropriate lane markers in green, and it's also highlighted the vehicles in green, because they're also significant to your driving since the vehicles are in your way. But notice it doesn't actually color these lines in green, even though they're still white lines. So what's going on here is that the neural network knows those are appropriate for driving, but it's just going to drive over that, so it's okay.
So let me understand, so what you can do is, right, when you're looking at the output response, you try to work backwards to see which input generated the strongest
Yeah, you
reads
work backwards to the original
thing.
image, and you say, what was here that caused this
Because one of the
response?
criticisms of machine learning is you can't tell what's actually happening. But
Yeah, that's,
this way is a nice.
yeah, they're not black boxes. You just have to work harder to figure out what's going on. And so, of course, I'm saying this is what it's doing, but this is what I infer it's doing. But what's important is that the features it's looking at are appropriate features, right? It's not looking at just this median here and like that median there and some sine wave back there. It's actually looking at the things I would look at. So I'd say, oh, it's probably going to learn something good. And so remember, none of it's hand coded, so it's all statistics. What did it think was statistically
So
important?
how do you work this backwards in the network? How do you get these features?
So we actually have another paper on archive, but so you have those. So each of these, as you go, there's some output from each layer, and you starting from the end, you go backwards. So you say, here were all these outputs, and I go backwards, and I say, from what inputs were these excited? And then I go backwards, I say, from what inputs were these excited? I go back, 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 and then you get to the actual input image, and you say, from what pixels?
But you have to store intermediaries, right?
Yeah.
Yeah, you can't, I mean, otherwise you can't.
Yeah, it doesn't, we can do it, we do it in real time, like
This
it's
is
not a
offline.
costly.
Sure.
Oh, real time?
Yeah, it's all real time. There's no, I mean, there is some cost to doing it, but it's not, it's not really expensive.
I mean, you can't just take the output and then say, oh, this came from this.
Yeah, you can, because the output's just a number,
Exactly,
right? So
that's what I'm saying.
yes, but with NVIDIA's GPUs, this is an easy task to do in real time.
Okay.
So you see, it still identifies practical features on the road, so even if there are no lane markings. So notice it doesn't care about the road itself, so it successfully identifies what things demarcate sort of the border of the road. So it identifies these vehicles and maybe the curb over there, like this trash can. Those are the important things to pay attention to, not like some random, like not this line in the middle of the road, so the crack in the road, it knows that's not important. Same things with sort of messy images. So here it's sort of a tougher road because it's more vague, so you see that it's lighting up more random things, or more seemingly random things. There's actually an intersection here, so it's identifying the lines from the intersection as well.
So, okay, go ahead, I'll ask the end.
So anyway, so just a quick video of that visualization of driving. So this is, I think, on the Garden State Parkway. So it's basically activating on the different lines as you're going through. But notice it doesn't light up on the tar. So in very, very bright light conditions, in the same places where you might get confused a little bit, you'll see some activations on other items. But for the most part, it'll always pay attention to the lane markers. But also the lane markers close to you. It doesn't care about the ones all the way across the road. Right? So this is a good thing to see. It says that the network probably learned to look at the same kinds of things we would look at, so I have some amount of confidence that it's going to do the right thing. And then at CES, at the beginning of the year, we had this big demo. So I have a long video so I can explain what's going on. So we have, so this wasn't on a public road, so there's nobody in the car. And then we gave people rides in the demo. We just had them get in the car, and there's an emergency braking thing that can hit the brake. So you see there's some buttons on the car that you can hit to make it brake. And someone's always holding an emergency braking, it's not a controller, but it's a wireless brake. Turn it on and off. But basically,
You trust wireless?
actually it's encrypted. It's been used for like 20 years. It's like really solid. Developed by these people who do encrypted communications for the military. Anyway, so it's a reliable safety system. But what we did with this is we trained the neural network to go around this course, through dirt, through other things. And we also trained the neural network that if the traffic sign is there, it takes this bypass along the cones. So what we were trying to show is that the neural network is able to make a decision. So even though there's just one output, it's able to do something that we would consider as a hard decision. Do I keep going straight, or do I now do a different behavior, even though the only thing that's different is one different thing is in the road? Actually, the cool thing about it, I don't think I have a video of it, but after we trained it with the sign, we could actually put a cone in the way instead of the sign. It would still take the bypass. So there is some level of generalization to it. So this is actually what we think is a pretty powerful technique. Anyway, so we went out to CES, and basically the week before CES, we drove the car around in circles to train it in different lighting conditions. And then during CES, we gave people demos in the car. So this is basically what the car is seeing. So you can see the road conditions were changing because it rained one day, and then other days it was bright and sunny, and then other days it was overcast. But the neural network, once it's learned to do the task, it does it very repeatably. So I think
this is a very simple case.
this is a very simple case, but so the thing you have to remember is that all of this is learned. Right, so if I had a map, I could do this with no problem, and I wouldn't hesitate at all. But the point here is that we showed up with a network that was completely blank. Right, and then we drove it around in circles.
You guys arrived a week earlier.
Yeah.
So we trained it for a week.
Yeah, we trained it a week because we also had to set up the Audi car, which didn't work at all at the beginning of the week because we'd never driven it before. And also the course kept getting ruined by things like there was wind one day that blew away the course. So, if you're setting up a demo, there are lots of risks that can happen.
So how much computing power do you need for this demo? Like what kind of computer were you using?
So there's this Drive PX, it sits in the back of the car. The network takes a millisecond to process a frame.
But is it like a GPU? I mean,
Yeah, it's a GPU. Everything is a
Is it
GPU.
like a GPU board, like a gaming GPU, or is it like?
No, it's like a little embedded computer like the TK1 or the TX1.
So it's like one of those little, okay.
Yeah,
like
it's a little embedded thing. This one is overpowered as 2 GPUs. We have another one that's 1 GPU.
I think the infomercial says computing power of 100 MacBook Pros or something like that.
Yeah, 100 MacBook Pros in your trunk. That's what a CEO likes to say.
Well, that's what I was kind of getting at.
I
Is
have-
it like 100 MacBook Pros or a little embedded?
Yeah, so they measure
It's
like
a-
the flops of operations.
It's a
it
little
does,
embedded
so,
computer
yeah.
with 100 MacBook Pros.
It's a,
But it's not like one of these 300-watt gaming machines.
It's a
No,
P100.
it's like half a horsepower or something. I think so. If it was running full out with both GPUs and everything going, it's like half a horsepower. And we take, like I said, 1 millisecond to actually do the propagation for a frame, so we actually are taking less than that. Anyway, so it does work more than just on demos. So at some point we trained only using sunny California data, and here it is driving on, I think, the Parkway in the rain. Anyway,
I'm
so
sorry.
ignore the voices. But the point is that we can take data from like a sunny condition, right? Only sunny daytime California on completely different roads, and drive it on roads it's never seen before in the rain with the windshield wipers on. It's still driving, right? So again, we think that machine learning will allow very rapid prototyping or very rapid development and prototyping of these systems. Whereas if you're hand coding a system, right, when the weather conditions changes, a lot of times you have to recode things like, oh, this is what it looks like at night. This is what it looks like. This lighting and that lighting. Whereas this is able to generalize in a much more powerful way.
So could you crowdsource that data?
So that guy George Hotz, who made Comment.ai, he tried to, and then I think he then sent out basically a job posting for somebody to correct cameras from one type to another. So the problem is if you start off with a system that's really hastily thrown together, it's very hard to put all the data together. So for instance, if you have, like, all the cameras are placed somewhere different, like the camera's actually on the right side of the car instead of the center, you have to know that. So it's something that theoretically you could crowdsource, but then you'd have to get the people that you crowdsource it to actually give you good data,
Okay.
which is...
I just wonder how robust the networks are to like data that's not that good, so.
Well, so for reference, when we first trained the system, we started off, and actually I think some of you guys saw this, we put a roof rack on the top of a Ford Focus, and we put some GoPros on it. And we put like this commodity USB, or sorry, Bluetooth to OBD2 port dongle into the car, and we recorded our steering angle from the OBD2 port, and we time synchronized the steering data with the cameras by holding up the cell phone in front of the cameras at the beginning of the recording session. And we were able to train a network that could drive the, we couldn't drive using the GoPros, but we were able to drive on a different camera with this little robot that we had. So it's fairly robust, but I mean, you do have to do lots of things to like correct the perspective, right? Because the height of the different camera is somewhere else, so the images do look different. So there's a bunch of completely, let's say, I don't know, it's not boring, but a bunch of like nitty-gritty things that you have to correct, like, oh, the slant of the camera is different, so the angle is different, the height's different,
If
so
you
the
had
perspective.
enough of the data, could you just cross-train over all of them and get something that's general enough?
Yeah, theoretically, you might need a bigger, more powerful network. I mean, the problem is, like, theoretically you could with any of these things, but why make it harder than it already is?
I guess Google might be able to do it.
How do you get, how much data do you need to train?
Did that say how much data we had? I think this was with...
No, not for a demo, for real world.
Well, it's driving the rule.
To drive better than me.
So it depends on the situation.
Under all conditions, drive better than
Well,
me.
but drive better than you where?
Snow, darkness,
No, but where?
accident.
But where? New York City or on the
Anywhere.
Parkway?
Anywhere.
So anywhere, that's a lot of data, right? Because anywhere includes Bangalore, right?
Let's say anywhere in the US.
Beijing.
Okay. So anywhere in the US is something more feasible. So I could start guessing that that's probably, I would guess, tens of thousands of hours, but we don't know yet.
So just a data point, right? I don't think Beijing, actually maybe I shouldn't speak for Beijing, you can speak. I don't think you should include places like India in any of this, right? Because this all is premised on the fact that there are rules and people follow rules.
Yeah. So it's another,
So
yeah.
in India, right, you kind of look at each other and figure out who goes first.
Yeah. Yeah.
You
So
guys know what I'm talking about? So,
yeah, the
Yeah,
solution
these
somewhere
photos
else may
from
be a
China.
different solution.
right,
Yeah.
so that's what I'm trying to tell you, right? So you have to kind of look at each other and say like, am I better than you? Yeah, I'm going to go ahead.
Well, so one nice thing about the car is
So-
is our
so
neural
none of this
networks
works.
know no fear.
I'm telling you.
No, you say 10,000 hours, right? If you think about this, I would want the system to be more reliable than myself.
Yeah.
To trust it, right?
Mhm.
And
Or your teenage child.
unfortunately, in the US, we don't have great data on number of accidents per mile because many accidents get unreported.
Mhm.
What we do have great data on is fatalities per mile driven,
Yeah.
right? Because all of those get investigated and reported.
Mhm.
So the average driver in the US does 100 million miles per fatality.
Mhm.
And that includes those guys who are drunk, those guys who are totally tired,
Mhm.
and every other crappy driver you can imagine of.
Mhm.
So a good driver, which of course we all are, probably does somewhere at the high end 1 billion miles, right, per fatality.
No, I doubt that. I think we're all average.
We're
I think we're all
He's
average
trying to be
drivers.
polite and not call us drunkards, okay?
Okay. Well, I think accidents happen.
Speak for yourself.
think of above average driver. It's somewhere in the range between lower bound is 100 million, and the upper bound is 1 billion. Right?
Okay.
Somewhere in that range, right? And let's say you want to actually be at the higher end. You want to be above 500 million miles. Now, how many miles do you have to test to demonstrate that you can drive 500 million miles without a fatality?
So again, this has to do with where you're showing you're testing it. So, like I said, right now our network, which I know isn't ready, could go all the way up and down the Parkway. Right, so I think you have to choose test cases that actually, so this is the case where a domain expert would come in. Right, so I think some of this is actually a collaborative thing, so I think it would be nice if people did a better if you track where accidents happen and how they happen, you could always try to simulate those accidents, or if it's simply a road condition, you could record that road condition. So we should have better statistics about where do humans make mistakes, so that we could actually test the cars on those particular accident-prone areas. The other thing you can do is, again, simulation doesn't prove anything, but I know some companies want to do photorealistic simulation and then do millions of miles of driving in photorealistic simulation, which is another way you can try to do it. And another way to do it is what we're doing. You collect enough human data, and then you use that human data, you hold some of it out as a test set. So you exclude those roads from training, you don't use any training that goes over those roads, and you do basically an emulation of a drive in those roads, and you could do an arbitrary number of miles, you just have to have a human drive those miles.
Right. I spoke to some car company representatives. They're thinking you may have to test for a couple of billion miles for one system.
Sure.
And
Yeah, but
Maybe.
but if you have good
seems
data on
like seems like too much if you want to repeat that for every model of automated car that comes out, right? So
But if it's
you have a
automated, then
No, but if you have the fatality data,
Right.
you can force the network into a scenario where that fatality occurred, right? And then
Yeah.
you don't have to test on the billion miles of the boring
Yeah,
I mean,
parkway.
the fact
But
of the
you
matter
do it at
is,
the
you
light,
have-
the
No, but that's-
traffic
You have a
intersection that's hard.
good representation of difficult cases,
Yeah,
right?
right,
Yeah.
but if you
Test
have
that.
fatality data, you
Right.
can get that
yeah,
representation.
and that's more fair, because the majority of the miles we do are miles where we wouldn't die if we had an accident. Like, you're going 25 down a residential road, there's no way you can kill yourself going 25, unless you go over a cliff. You can kill other people, but,
Right, the Turnpike and Parkway are some of the safest highways in the United States.
yeah, because they're
Parkways?
highways, I mean,
Yes.
Turnpike,
yeah.
because it's easy, so most people get
easy
into
driving.
accidents close to home.
Or like
It's the
intersections and
Oh,
stuff.
that's so counterintuitive,
Yeah.
that's fine.
But
If
no, so-
you drive
so-
out west, there's so many people that are falling asleep and running off the road and killing
Yeah.
themselves.
Sure. So what about differential learning? I mean, is there any way that you can make this sort of, okay, you have I don't know, 200,000 miles on highway,
Yeah.
and then you say, no, but now I need really to capture all these weird corner cases and incrementally.
Well,
build-
so,
Because, this
Yeah, you could
implies
con-
that you start from scratch always.
we do that now because training it doesn't take that long. If
I know,
training,
but
if
I'm
training
saying
took a
that-
month, then yeah, we continue training the existing network. And so at some point, if the feature extractor is not learning any new features, it's just new combinations of those features, then yeah, if you continue training the existing model, there's no reason to start over. Yeah.
So let me ask about academic questions. If these cars suddenly can talk to each other, will that be beneficial?
If all cars could all talk to each other, it would be beneficial, but the problem there is all
In
car
what
companies,
So how much benefit do you think it will get?
it depends what data they can transmit. So one thing that would help is just traction information. So let's say you sent the car behind you traction information. But then you have to also know what's the wear level on everybody's tires, all those things. So it's a information question. So the more information you have about everyone else's car. So for instance, I'm driving behind someone and they shared,
But I
I
don't need
just
to
slipped,
know about
my tires
you.
are 2 months old, with treads that are this big, and the weight of my vehicle is this. That could be useful to me, because then I could calculate if my car would slide too.
But even before that,
Yeah.
what about if your scheme can have access to that type of information from within your own vehicle?
So this again, so how useful, let's pretend you were on a cell phone with the person in front of you, how useful would it be for you to be on the cell phone with them? So I think it would be as useful in the same situations. So if the person could say, I just saw a deer, right, then yes, in that case, you sending me your images,
No,
so
but I
my
meant by
network can
that-
look at them.
Well, my question was somewhat different than hers.
Okay.
Hers was communicating between vehicles, mine was
Yeah.
actually just getting all the sensors from within a single vehicle. Like, for example, would that affect your decisions if you knew that the road slippage coefficient was particularly low today?
Yeah.
Or high today?
Yeah. And that's why, so like the other sensors we use are like the IMU in the car. So see, like because the steering wheel isn't, as we all know, how you actually turn, right? So if you're in the snow, for instance, you could turn your wheel quite a bit and still be going straight forward. So we actually look at the inertial system.
So what's the role of stereoscopic image? I mean, humans need it,
It's,
but it's not
I
clear
don't need
that
to drive, I
this
can
needs
drive like this.
Try. I want you to park.
I know, I have
with one
tried
eye,
it.
yes.
I have tried it because we talked about it, it's fine.
You can park with one eye?
Yeah, why not?
Okay.
Stereo doesn't work more than 6 feet out.
That's what I'm saying, parking is, is a tricky part.
So when,
Try shooting a ball
Yeah,
in the
but
basket
parking,
with one eye.
parking is actually a solved problem because you just use ultrasonic sensors, then you can't hit anything. Like you can't mess that up.
No,
Cars
that's
today
okay,
you
if you
can
have
buy
the other
these,
sensor
but-
input, which actually brings me to another
Yeah.
question. What if you have multiple outputs?
We've
Right.
had multiple outputs, so we do like a lane change. That's
No,
multiple
but I'm
outputs.
saying, how do you discriminate between braking and steering?
Oh, you just have multiple outputs, and they're trained with different labels. It just works.
So
So-
how do you decide that steering is better than braking?
Well, it always does all of them, so it still steers while it brakes.
No, but I mean, so that's actually my question. I mean,
Yeah.
quite often I would speed up actually,
Well,
to
so that's
avoid the problem.
So that's all interior to the network. So we would make a decision about whether it's going to stop or whether it will go around. So right now we train it to, we only use data where we stop.
That's what
because
I'm
for
asking.
training-
So what happens if you have
So-
multiple training?
Well, that's a choice of the data you give it. So whenever we have the option, we choose a more conservative driving style. Because we care more
But
about
that's
safety.
a more conservative driving style in training, right?
Yeah. Well,
But that can be deadly. I mean,
Well, so a more conservative driving style is in, so if you're in a rush, somebody's making a left turn, you go on the shoulder and you go around them. So we would prefer that the neural network stop. And if you look and you make sure it's actually safe here and it doesn't break a law or something, then you do it.
No, but I'm talking more about, so say the car is, you see it's gonna bounce back at you, right? You would speed up to avoid it rather than braking. Because you're
What do you
gonna
mean
get hit.
car's gonna,
So if you see somebody bouncing off of the sides of the road,
oh, you see like somebody driving erratically.
or even having an accident, right?
Yeah.
I mean, if you just do the simple thing, which is braking, you might actually get in trouble.
So this is where we get into liability things. So let's say you attempt to dodge it and that causes another accident, you'd be liable for that, whereas if you brake and then you hit it, you're not liable. Right, the other person
Trolley
caused the
problem.
accident. Right, so this is.
I mean, I'm talking about not getting killed, I don't care about.
No, but-
Yeah, but it's a question of who pays for it.
Yeah. So actually, so the problem is the question you've asked me deals not with an engineering thing, because we could train it to do one thing or the other, but it comes down to probably a legal requirement. What would you be required to have the system do?
So that's my question, how do you account for that? I
Oh,
mean,
so then
that's not in the
well, so then
training, right?
you have to choose what training data to give it.
I see.
So that's
So you're actually pushing everything into training.
yeah, and you have to give it. So if you want a certain behavior or don't want a certain behavior, you have to take it out or make sure it's in.
So I want to recap a bit what you were saying, because I think you kept saying that you're advocating machine learning, and I think you were advocating deep learning. You learn the features while
Yeah.
the others
Well, I
are
guess
doing
we're-
machine learning
Well,
as
yeah,
well.
we're advocating, I guess, end to end.
Yeah.
So we're advocating that pixels in, steering out, rather than chopping it up. And at its simplest form, I guess what we're advocating is, if you have some amount of error in your decisions and then you do 10 different things, right? Then you have a chance to make a mistake at each section, right? Why would you break that up instead of keeping it in one place?
Right, but also the trade-off is that you need to have a lot of data so you can have the big network.
Yeah, but it turns out those classifiers that people are using, even when they're chopping it up, they need more data that's more expensive to get. So they have to actually label every single curb, every single lane line, every single pedestrian, every single bicyclist, and that actually literally means a person advancing one frame, drawing bounding boxes, tracing the lane line, advance one frame, draw bounding boxes, trace the lane line.
No,
So
I
their data
think-
is much harder to.
Well, I think, that's a really interesting point. So they need more expensive data, but they need more data. So you're gonna get a lot of data that is cheap,
Yeah,
right? And that's a good thing.
yeah.
But do they need,
I think they must need less. But as they get to, let's say you need more classes. So actually the group in Santa Clara, at some point, there's one of the things they want to do is they had to identify like motorcyclists. This meant somebody had to find a motorcycle parade, and I'm not joking. They found a motorcycle like enthusiast something or other. They drove there to drive around where there would be more motorcycles. So by expensive, it's not just somebody has to label it. It means you have to figure out where that data is going to be and go there, which makes it way more complicated.
So I think we can take all the other questions offline.